the Kirchhoff current law. It says that the algebraic sum of all the currents entering or leaving a point is equal to 0. This may be the one definition of KCL, and we can have another definition. The algebraic sum of all the currents entering to a point is equal to leaving a point. We try to understand about these two definitions by using one point that is connected to several branches. Consider this point. There are several branches connected to this point as shown here. These are the resistances of these branches. Consider I1 is entering to a point. I2 is also a current that is entering to this point, and let's suppose I3 is the current that is leaving to this point, and I4 is a current that is also leaving to this point. So we apply the first definition of the KCL, that is the algebraic sum of all the currents entering or leaving a point is equal to 0. That is, mathematically we can write this as I is equal to 0 to m, and I of m is equal to 0. This shows that the algebraic sum of all the currents entering or leaving a point is equal to 0. So we apply this definition to this figure, that is I1 plus I2 plus minus I3. Minus means that this current is leaving to a point, plus minus I4. Minus I4 means that this current is also leaving to a point, that is equal to 0. So by rearranging these terms, we can have this following equation: I1 plus I2 is equal to I3 plus I of 4. From here we got another definition of KCL, that is sum of all the currents entering to a point, which are I1 and I2 in this case, is equal to sum of all the currents leaving to a point, which is I3 and I4 in this case. We take an example in order to further elaborate about Kirchhoff current law. You can see in this example, find current across resistor R3 if it is known that the voltage source supplies a current of 3 ampere. So you can see this circuit, this is the voltage source that supplies a current of 3 ampere to this circuit, and we need to find the current across this resistor R3, while we have the 5 ampere current source as well. So we need to redraw the above circuit once again so that we can apply Kirchhoff current law easily and can find the current across resistor R3 as well. So here we go. This is R1, okay, and the current across the R1 is IR1, let's suppose. This is R2, and the current across this R2 is IR2, let's suppose, and this is IR3. The current across resistor R3 is IR3, suppose. This is R3. And the current supply and the current supplies by this 5 ampere source is, let's suppose we show it by this 5 ampere, right? So this is the point, and we need to apply the Kirchhoff current law here at this point. So let's talk about the current entering and current leaving to this point. IR1 and I5 or the currents entering to this point, while IR2 and IR3 are the currents leaving to this point. So let's apply the Kirchhoff current law on this point. IR1 plus I5 ampere, these are the currents entering to a point, is equal to IR2 plus IR3. These are the currents leaving to a point. Okay, so IR1, according to the above question, this is 3 ampere plus I5 current is 5 ampere, is equal to, this is IR2, so IR2 is actually 5 ampere plus IR3. Okay, after solving the above equation, IR3 we get is equal to 3 ampere. So you can see that we can apply Kirchhoff current law on any point and can find the current across any branch very easily. We take another example in order to further elaborate about Kirchhoff current law. We take this circuit, and you see that the 18 volt supplies a current of 8 ampere to this circuit. So we need to find RA, this is RA, using Kirchhoff current law and Ohm's law. So we redraw the above circuit in order to further elaborate about KCL. We need to mention the current supplied by this 8 volt source, that is 8 ampere, and this is IRA, this one is IX as it is shown here, and we need to mention the current supplied by this voltage source, that is 13 ampere. So we apply Kirchhoff current law at this node. So let's see, 8 ampere is the current entering plus 13 ampere is the current entering to the node, that is equal to IRA, which is the current leaving to the node, plus IX, which is the current leaving to the node as well. So you can see that we need to find IX using Ohm's law first, and then we need to find IRA. So IX according to the Ohm's law can be equal to 18 volt source over 6 ohm. As you can see that across the 6 ohm resistor the voltage is 18 volts, so that is equal to 3 ampere, right? So we put the value of Ix in the above equation A, and then we find the value of RA. This is 21 ampere, and that is equal to IRA plus 3 ampere. Hence IRA is equal to 18 ampere. The question is we need to find RA. This is RA. So RA can now be equal to the 18 volt over 18 ampere, and that is equal to 1 ohm. So you can see that we can easily find the value of RA using Kirchhoff current law. In my next videos, we will apply Kirchhoff current law in further examples. Thanks for watching this video and have a nice day.